Hello, grade 12s, and welcome to question 2 of this paper. So, in question 2, the first question we have for 2.1 says, the following is an arithmetic sequence. And we have 1 minus p, 2p minus 3, and p plus 5. 2.1.1 says, calculate the value of p. Okay, so the big hint here is that they said this is an arithmetic sequence, and there's something that we know about an arithmetic sequence. So if this is the sequence that we have, every arithmetic sequence, right, would have a difference. And that difference is constant all through. So when I'm trying to find this difference, the way I'll find it is by saying the next term minus the previous term, because this is arithmetic. So that minus that, and that's going to be the p plus 5. Now you see we're subtracting by something that has two terms. So you need to protect this with brackets. So 2p minus 3. And then we're also going to find the difference here. That minus that, second term minus first term. So that is 2p minus 3 minus, again, bracket 1 minus p. So this is the difference, and that is also the difference. But because it's arithmetic, the difference needs to be constant all through. So it means that these are equal to each other, so we can equate them. So this is our equation, and it will help us to solve for p. Okay, so let's simplify. We have 2p minus 3. If we distribute, that gives you negative 1, and plus p is equal to p plus 5, and that will give you negative 2p plus 3. Okay, so just simplify. I actually prefer simplifying things with the p's first on the hand sides that they are. Okay, so on the left hand side, that would give us 3p, and that gives us negative 4. Okay, it's equal to, and then here p minus 2p, well, that gives you a negative p. So let me just start with the numbers. 5 plus 3 is 8, so that's 8, and minus p. Now we can take the p's over. So that is 3p, and this comes over and becomes a positive p. 3p plus p gives you 4p. So we have 4p here is equal to, we still have the 8 here, and if the negative 4 comes over and becomes a positive 4, 8 plus 4 is 12. And then we can divide both sides by the 4 to get rid of that to solve for p. So therefore, p is finally equal to 3. And there we go. So that is the solution for the first question. And we move on to the next question. Okay, so 2.1.2 now says, write down the value of, and the first one, we need to find the value of the first term of the sequence. Okay, so since we know p, we can find the first term. The first term, t1, is this. It's 1 minus p. So if t1 is equal to 1 minus p, then, okay, this is a, so we don't forget. So then you just substitute p. So that's 1 minus 3, which is negative 2. So that is the value of t1. And then b says we need to find the common difference. Okay, so there's not much work we need to do here because we already found p. So do you remember when we said t2 minus t1, right, would give you a common difference? That is a common difference. And t3 minus t2 also gives you a common difference. So all we have to do is take a simplified version of the common difference. So remember, that is when you didn't take anything over yet. So that was a common difference. When we simplified it, it got to this point. Okay, we didn't take anything over at this point. But then this one looks easier, so I'd rather use this one. So this is actually the value of d if you just substitute p, okay? Because that minus that, and then you just simplify that. So that is d. So you can just go ahead and tell them that d is equal to that 8 minus p. So 8 minus p, but we know what p is, 8 minus 3. So d is finally equal to 5. And there we go. So that is t1, and that is the common difference. Okay, moving on to the next question. Question 2.1.3 says, explain why none of the numbers in this arithmetic sequence are perfect squares. Okay, so why are none of the numbers in this arithmetic sequence perfect squares? Let's go ahead and just expand that arithmetic sequence. So we know the first term is negative 2, and the constant difference is 5. So we just keep adding 5 to get the next term, right? So if you add 5 here, negative 2 plus 5, you're going to get 3. And then again, add 5, then we get 8. And then keep adding 5. Let me just write the next term. So again, plus 5, we're going to get 13. And then again, we get 18, then 23, then 28. But do you notice now, I've actually done this question before. It looks like they're recycling a question because I remember this, but I just don't remember exactly where it was. I'm going to look for that quickly. Okay, I didn't really find it, but I know I've done this question before. I can remember this exact question. Okay, so we have this, and then of course, if you keep going, you're going to end up with 33 and then 38. So the question is, you need to explain why none of the numbers in this arithmetic sequence are perfect squares. And I remember how that question was phrased. It actually asked, you need to, well, it wasn't asking, it was just asking you to prove that none of the numbers would be a perfect square. So, but this one, we just have to explain why. Okay, so let's look at this. Let's actually focus on what exactly perfect square numbers look like. If you have a perfect square, right, those numbers would work like this. If you take 1 squared, you get 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. And then 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100, right? And let's just end at, I'm just trying to just see exactly what these type of numbers look like, and then let's just compare them to this so that we can understand why none of this would ever be a perfect square. So 11 squared is 121, and then 12 squared is 144, 13 squared is 169, and I think here at this point it's fine. Let's go ahead and look at these, right? What do you notice about these numbers? -2, 3, 8, 13, 18, 23, 28. Do you notice that all of these numbers, of course, except for -2, right? All of these numbers, they end either with a 3 or with an 8. See? 3, 8, 3, 8, 3, 8. And that will just keep happening throughout this sequence. So that's what happens, right? So let's actually go ahead and look at perfect square numbers and find out why exactly none of this would ever be a perfect square, because we can see that these numbers keep ending in a 3 or an 8. Well, with perfect square numbers, we can also just look at the numbers that they also end in. So perfect square numbers, they end with 1. You can have a perfect square number ending with 1. And we can also see that same thing happening here. That ends with 1. That also ends with 1. Okay, so 1 is one of the things that perfect square numbers end in. Do they end with 2? No, but we don't even have to consider 2 really. I guess we just have to focus on whether we can ever have a perfect square number that ends with a 3 or ends with an 8. Okay, so the next type of number that will end with, let's try 3. Do you see any perfect square here that ends with a 3? No. And if you keep going on, even if you said 14 squared and 15 squared, they will never end with a 3. And again, what other numbers do they end with? So do they end with 4? Yes, they do end with 4. So perfect square numbers end with 1. They end with 4 as well. See, that ends with a 4. That also ends with a 4. If you keep going, you will also find more perfect square numbers that end with 4. Okay, so they end with 1. They end with 4. What else do they end with? I also see they end with 5 as well. See, 5 ends with 5 there. If you kept going and you said 15 squared, then you get 225. And that also ends with 5. So perfect square numbers also end with 5. And do they end with 6? Yes, we have there 36. Okay, if you keep going, I think about like 14 squared ends with 6 as well, because 4 times 4 is 16. So they definitely also end with 6. Yes, we only see 1 6 here, but if you try 14 squared, it will also give you something that ends with 6. I know that because when you say 14 squared, I know that if you square 4, you get 16. So that ends with 6. So definitely 14 squared will also end in 6. Do they ever end with a 7? No, you won't really find a perfect square number ending with 7. So do we have perfect square numbers that end in with an 8? No, you will never find a perfect square number ending with 8. So that doesn't work. But you do find ones that end with 9. So that's 9. That's 9. That's also 9. Okay, so you get ones that end with 9. And then, of course, I would say 0 as well, which I should have put here because I'm just trying to put it in order. And also 0. And of course, this is because of numbers like 100 and 400. Okay, so those type of numbers. So these are the numbers that perfect square numbers end with. And as you can see, these ones, okay, they end with either a 3 or an 8, except of course for the -2. But -2 is not even a perfect square either. Okay, so our answer for this is the reason why none of the numbers, okay, in this arithmetic pattern is going to end with a perfect square is simply because perfect square numbers end with these, while these numbers in this pattern will always end either with a 3 or with an 8. Of course, that's excluding the first term. Okay, so my answer for this is because perfect square numbers end in these numbers that we spoke about, while all the terms in the pattern, excluding the first term, ends in a 3 or 8, okay? Because that one ends with a 2. So that is the answer to that question. That is worth 2 marks. This is a recycled question. They have already asked this question before. I've seen this question. So you see, past exam papers are very important to do, but make sure that you have used maybe a textbook or something to go through your theory first and then start working on exercises and then past exam papers. So in maths, just make sure you focus on practicing. That is very important. Okay, so that is it for that question. Moving on to the next question. And the next question we have 2.2 saying the following sequence of numbers form a quadratic sequence. Okay, so that's a quadratic sequence. And 2.2.1 says the first differences of the above sequence also form a sequence. Okay, think about what kind of sequence that forms. The first difference of a quadratic sequence will always form an arithmetic sequence. Okay, so that's what it forms. Then they want you to determine an expression for the general term of the first differences. Okay, so this one is relatively simple. It's not really a complicated one. So they're just telling you that you have this sequence, right? This is a quadratic sequence. And all they're saying is when you find the first difference, when you find the differences of this sequence, you're going to end up with another sequence. Now we know that when you find the first difference, it's going to be an arithmetic sequence. And you just need to find the general formula for that first difference, for that arithmetic sequence. That's all. Okay, so let's just go ahead and find that. We're going to say this term minus that term. So it's always the next term minus the previous term. So that's -11 minus -6. You know that that's going to become a plus, okay? So that's -11 plus 6. It's like saying 6 minus 11. And that's going to give us a -5 that we'll have first. Keep moving. And then we have -6 minus, of course, -3, which becomes a +3. So that's 3 minus 6, which is -3. Then -3 minus -2, which is really -3 plus 2. -3 plus 2 gives you -1. And then lastly, -2 minus -3. So -2 and becomes +3. So that is +1. Okay. So this is the sequence that they're referring to. That is your first differences. And you will notice that this is well, you don't even have to notice. We know that if this is quadratic, this is arithmetic. So we just have to find the formula for this. The formula of an arithmetic pattern is Tn is equal to A plus n minus 1 multiplied by D. So the first term is 1, as you can see. And your difference, you're just going to find by saying next term minus the previous term. But this one looks easier. So what's -1 minus 1? It is -2. So that's your difference. Well, I'm sure we're supposed to leave it somewhere here. So I'll just do that. It's equal to -2. Okay, so Tn is finally equal to 1 plus n minus 1 times -2. And then I guess you can simplify this if you want to. So I'm going to go further and simplify this. So this is Tn is equal to, and we can distribute. That is going to be 1, and then you're going to distribute that into here and here. So that gives you when you multiply, -2n, and when you multiply to the -1, it gives you a +2, which is really just Tn is equal to -2n, and 1 plus 2 is +3, and there we go. So that is the formula they were referring to. Okay, moving on to the next question. Okay, so the next question, 2.2.2 says, calculate the first difference between the 35th and the 36th term of the quadratic sequence. They keep bringing this question over and over again. Okay, they just keep representing it in different ways. So I want you to understand something about this. Remember, this is referring to the quadratic pattern. They want to find out what exactly is the difference between the 35th term, term 35, and term 36. What exactly, which term is going to be here? So you need to calculate the first difference there. What is the value of that? Okay, so please note that this is only for 1 mark. It's a very simple step, okay? It's not something where you have to go start calculating a lot of things. It's really not that at all. Think about it like this. Okay, if you have a quadratic pattern, and let's say I have T1, T2, and T3. Okay, if I wanted to know what term exactly would be between the third and the second term in this quadratic pattern, which term would this be? In your first difference, of course. In your first difference, this would be term what? Well, if you say term 2 minus term 1, you'll get term 1 of your first difference. And if you say term 3 minus term 2, you'll get term 2 of your first difference. So the term between term 3 and term 2 in your quadratic pattern will be term 2. Look at the pattern going on. If you're trying to find the first difference term between two terms in your quadratic pattern, if this one says 3 and this one is term 2, then it's always going to be the second one's term. Okay, so what I mean by that is we have a 2 here and we're going to also have a 2 here. So think about it like that here. If you have term 36 here and term 35, which term in the first difference would be right between the 36th and the 35th term? It will be the 35th term in the first difference. That's just how it's going to always work. Okay, because you will notice that your first differences, they would have one less term than the amount of terms in your quadratic pattern. So this is actually really simple. That's why it wasn't something that you had to like over stress about. I didn't even need this diagram. All you have to think about is finding term 35 in your first difference. And we already have the formula of the first difference. So we're just going to substitute that. So it means that this is term 35 is equal to, and I'm substituting, it's negative 2 multiplied by 35 plus 3, because that is our term number, term 35. And that will be our answer. So go ahead and find that answer, and that's your answer. And that first difference is negative 67. And there we go. That is the answer to that. Moving on to the next question. The next question, 2.2.3, determine an expression for the nth term of the quadratic sequence. Again, they're being very, very simple and straightforward. So we just have to find the quadratic pattern's formula. Okay, let me bring that quadratic pattern down. So we already have this, we have the first difference, and we already know what the second constant difference is. It was negative 2. We found that already from here, okay? The second constant difference, that minus that is negative 2. We found that. So we're just going to go ahead and find the Tn formula. Remember that the formula for your quadratic pattern, the general formula of a quadratic number pattern is Tn equals an squared plus bn plus c. So we just need to find A, B, and C. To find A, or to find all of them, we're only going to use the first term of each of the patterns that we have here of the quadratic first difference and the second constant difference. So to find, let me actually just move this to the side. Okay, so to find this, the A, you're going to equate this first term here to 2A. And then to find the B, you equate this number to 3A plus B. And to find this one, you equate it to A plus B plus C. Okay, so that's what we have there. So we're going to go ahead and tell them that 2A is equal to negative 2. Solve for A, and we'll divide both sides by 2. Therefore, A is equal to negative 1. And then to find B, we're going to say 3A plus B, but we already know what A is. It's negative 1. So 3 times negative 1 plus B is equal to our 1 over there. Okay, then we know B is equal to, then we have 1, and 3 times negative 1 is negative 3, right? And you're taking that negative 3 over and becomes a positive 3. So 1 plus 3 is 4. And then we have C as well. I'm just going to go ahead and substitute. So that's A plus B plus C. We already know A, it's negative 1. We know B is 4. And we don't know C yet. And it should be equal to this number over here, which is negative 3. So it's equal to negative 3. Let's just go ahead and add. So C is equal to, we still have negative 3. If you say 4 minus 1, because that's really what it is, 4 minus 1 is 3. Take your 3 over, your 3 becomes negative 3. C is equal to negative 6. So there we go. We just have substituted into this equation. Tn is equal to negative, okay, since it's negative 1, just call it negative n squared. And we have plus 4n and then minus 6. And that is our formula. Simple like that. And we move on to the next question. Okay, and the last question for question 2, 2.2.4 says, show that the sequence of numbers will never contain a positive term. So in a nutshell, they want you to show them that the sequence will always, all the terms in the sequence will always be negative. That's all, really. Okay, so that's really all they say. Negative terms. That's all we're going to always have. Okay, because this is a quadratic pattern, right? When we already have the formula of the pattern, I can say that there are two ways of really proving this, okay? And I'll show you the two ways just so that it is both there, okay? The one way is a little more graphical. You just have to use like a diagram to explain it. You wouldn't need to draw the diagram maybe in your answer, but I will use a diagram just to explain what I mean by that. So let me go ahead and explain two methods of doing this. So the first method would be really just looking at the arithmetic part of this formula. And the reason we are using this is because we're trying to show them that all the terms in the sequence are going to be negative, right? So because this is going to control your term values, we're going to use that. Okay, if you substitute an n value, you get a specific term value. If you substitute another n value, you're going to get another term value. So that controls the term. So we're going to use that in both of these methods. Okay, so the first method, we're focusing on really just let's call it the arithmetic of it. We're looking at the way the numbers look and what creates a positive number and what creates a negative number. That's really what we're going to look at here. So in the first method, I need to show them that it's always going to be negative terms. So I can take advantage of the fact that this is a quadratic expression that we have. For you to find out the kind of results, okay, the type of numbers you're going to get if you substitute n values into a quadratic expression will be, the best way to actually find out that would be to manipulate this. And we call that, or to simplify this, we call that really completing the square. So we're really just rewriting this in a way that we would be able to see the nature of the result of this expression. So completing the square would be this. So we take Tn is equal to, and we say negative n squared plus 4n minus 6. The first thing we're going to do here is, so we're really just putting it in turning point format, really. Okay, turning point format is very helpful because it helps you to figure out exactly what the nature of the terms would be. So we're completing the square. You need to first of all ensure that the coefficient of n squared is a positive 1. Right now it's a negative 1, so we're going to take that out as a common factor. So we're taking that negative out and we'll be left with n squared, and then here you're left with negative 4n and positive 6. Okay, this is what we have now. Then after taking that out and ensuring that the n squared has a positive coefficient of 1, you are going to take now the coefficient of n and you're going to half that. So you're going to multiply that by a half. And of course, when we do that, we get negative 2. And you're going to square negative 2. Now, because we are dealing with this as an expression and not an equation, what you're going to do with this negative 2 is you're going to add and subtract negative 2 to this expression. The idea behind that is you're not changing the value of the expression, you're just changing the way it looks so you can better simplify it. So we're saying this is equal to negative, and I'm going to use big brackets now because I can see that I have brackets here. So I have n squared minus 4n, and I'm going to go ahead and add the negative 2 all squared, and then subtract it. So that this way I'm not changing the value of the expression. So minus negative 2 all squared. And then I still have my plus 6, of course, and close bracket. Okay, then at this point, we're just simplifying. We have our negative outside, open a bracket. And what we're going to do is we're going to pull, because this has a squared and that has a square, we're going to put the n and the negative 2 into one bracket. So we're putting them like this, and we're saying that they're both squared. And what we have there is n and the minus 2. Okay, then after doing that, we're going to just rewrite what we have. You see, this is all that is left. You can simplify that as a single number. That is fine. So negative, and we have, so that's minus, negative 2 squared is 4. So minus 4 we have there, then plus 6. 6 minus 4 is positive 2. Okay, so this is what we have here. Then lastly, you see these big brackets, they shouldn't be there. You need to simplify that out. So what we're going to do is take our negative and distribute it into our terms here. Notice please that we have two terms, this term and this term. So when you distribute that, this multiplies just to this bracket, not inside the bracket. So really all you have there is our final answer, Tn is equal to, the negative goes in front of that, negative n minus 2 squared, and then the negative multiplies into the positive 2 as well, and that becomes a negative 2. So this is what our expression looks like. And now we can actually look at this and determine the nature of this expression, meaning what kind of values will this expression have? Okay, so given that this is the formula for a pattern, right? You know the way patterns work. The n values of patterns, okay, the term numbers, they can never be negative. You cannot have term negative 2, for example. It's always going to be positive numbers. So term 1 and term 2 and term 3. So they're integers first of all, and they're always positive. So I know that I'm already putting these premises here. I know that n needs to be greater than 0 and n needs to be integers. Okay, so n is an element of integers. I'm just stating that. I know it's obvious, but I'm just going to put it there as well. So now we just need to show them that these terms will always be negative. For me to show them that the terms will always be negative, I'm just showing them that this expression will always have a negative value. How do you prove that an expression or a number is negative? How you prove a number is negative? Negative numbers are a result of a positive multiplied by a negative. So if I can show that there is a positive number that's been multiplied to a negative, then it's going to show that, okay, that is negative. So how I'm going to do this is I can just go ahead and take this expression as it is, and I'm going to examine it like this. Let's start with the part that is squared. You see, n minus 2 squared will always be greater than 0, or it could also be equal to 0. That's in the case where maybe n is equal to 2, right? So the 2 minus 2 would be 0, 0 squared would still be 0. So the expression will always be either greater or equal to 0, that part. But then, so this is already showing that this is positive or equal to 0. But then what happens is we have a negative in front of that. So if this will always be positive, it means that this, because you put a negative in front of it, it will always be negative. So it's either going to be less than 0 or equal to 0. I also have to consider that as well, because that could be equal to 2. So that is always going to be equal to 0 or negative. So what happens then when you subtract by 2, by something that is already either 0 or negative? It's going to become even more negative, because if it was equal to 0, if this expression, because we substituted a number here, was equal to 0, and then you subtracted by 2, so that's this part over here, then you subtracted by 2, it will make this negative 2. And then every other expression that you get will also be negative, okay? Because it's either going to be less than 0 or equal to 0, okay? So it means now that if you wrote the expression like this, let me just say negative n minus 2 all squared, right? Minus 2, it's always going to be negative, so less than 0. And this would really prove that. So it would mean that Tn is always negative. So that is just using the nature of the expression. Okay, that proves that that will always be negative. Okay, so that, I'll say that as one way of proving that. Now, the second way of proving this would be kind of thinking about this as a function, okay, as a graph. This is a quadratic expression. Because it's a quadratic expression, it means that we can represent it as a parabola. Now let's think about the type of parabola it's going to form. So when we have our axis, so this is our y-axis and our x-axis. First of all, let's just understand this. You see the values that will be on your x-axis. Those would be your term numbers. So like term 1, term 2, term 3, and so on, right? And then the numbers, so just say those are terms. The numbers that you'll have on your y-axis, those would be your term values. That is the result of substituting a term number into your expression. So I could also add numbers here as well. So let's just go ahead and say, let's say -1, -2, -3, -4, okay, and just 1 and 2. So what happens here is we're going to go ahead and draw this graph, but we're not going to overthink it because there's really just one point that we need on this graph to be able to see the kind of terms this will always have. And that term specifically that I'm referring to is going to be your turning point. You see, if your parabola is positive, it's going to look like that. And this is the turning point. The turning point is very powerful in telling you the type of values you're going to keep having for this. A positive parabola will always have whatever number that is, whatever y value that is, right? And everything above it, every y value greater than it. So in this situation, if these numbers were positive, of course, you would see that, okay, that will always have positive values. So if we look at that with this graph, let's go ahead and find that turning point or the maximum or minimum value. Because this is a concave down parabola, it's going to have a maximum, meaning this is the highest that the graph can go. Of course, the lowest of the graph would be like negative infinity because this graph will keep shooting down forever. So we can go ahead and find that turning point or the maximum of this parabola. And we can use the formula x is equal to -b over 2a to find that. I'll just call it n because we are working with terms here. So -b, you can see that the b value here is 4. So we have -4 over 2 and a is -1. So times -1. So that's really just -4 over -2. Which is +2. So that's what the term number at the maximum is going to be. That is this. That is +2, meaning our maximum is going to happen where x is equal to +2. But what we actually need is the y value of this. The y value of this we'll find by substituting that x value into your Patton's formula. Okay, so Tn. So what happens at where t is equal to 2, which would substitute like that. And we'll find out that T2 is actually equal to -2. So you see, the maximum is at -2. So here, this is what it means about it. Let me actually just tell them that the maximum is -2. And why this is actually very important to prove that these terms will always be negative. You see, if your maximum is at -2, it's 2 and -2, it's here. Remember that this is a concave down parabola. So it's going to look like this. Then you go like that and like that. Do you see that? Remember the y values tell you the results. They really just tell you what exactly your term values are going to be. For example, when n is equal to 1, your y value or your term number is going to be maybe something like -3. It may not be exactly that. Of course, it's just an example. And then where n is equal to 2, your y value is -2. Do you see that none of these y values of this graph will ever be positive? Because your positive numbers are here. There's no graph here. So it will never have a positive value. And we can already see that. So that's why the maximum is very important in proving what kind of term values you're going to have in a parabola, of course. So what I would just add to this is, because the maximum is equal to -2, and we know that the a value of our parabola or our formula is negative, we would know that this will never have a positive value. Rather, the terms will always be negative. So terms will always be negative. Always be negative. And that's how we would actually prove that. Okay, so there's actually two ways. You can visualize it and think about the nature of the terms, looking at it as a graph, or you could actually just think about it based on the nature of the expression. okay, and what the values of the expression are going to be when you substitute n. Okay, so that is it for this question 2. Then we move on to question 3. We are on question 3 of this paper, and question 3 says 3.1. Given Sn is equal to 4n squared plus 1, we need to determine term 6. Again, recycled questions. They keep recycling questions. This one has come up before. So, and this is really something that's actually in a textbook. The Kevin Smith textbook, grade 12, there's a question like this. It's an example, really. It's just to teach you how to work on questions like this. So I know that you see Sn is equal to, and you see something that is quadratic. All you have to focus on is the fact that this is Sn. It doesn't matter whether this is quadratic or not, because it's not even the Tn formula, okay? It's just Sn, and Sn stands for the sum of terms. So let me give you a quick illustrative example of how this is going to work. So we can think about this like this. You see, if I was referring to the sum of 2 terms, it means that I'm speaking about term 1 plus term 2, okay? And if I said the sum of 3 terms, it means I'm speaking about term 1 plus term 2 plus term 3. And that will be the sum of 3 terms. I can actually use this information to find term 3. Here's how we're going to do that. To find term 3, do you see that if you take the sum of the 3 terms, all of this, and you subtract it by the sum of 2 terms, all of that, look what's going to happen. So remember, we're saying S3 minus S2. What's going to happen is everything that repeats here will cancel, because we're saying this entire thing minus this. So T1 would subtract with T1, and T2 would subtract with T2. And what are you left with? Term 3. So that's actually what you can always do to find a term value if you're given the formula for the sum of the series, regardless of whatever series it is. Whether it's arithmetic or geometric, you can actually do this. Okay, so even if I asked you, okay, how would we find, let's say, the 11th term? You would find the 11th term by taking the sum of 11 terms minus the sum of 10 terms. You'll be left with the 11th term, okay? So that is really the reason why, because those same ones, they cancel since they are the same thing. Okay, so with that being said, we can easily find the 6th term since we know the sum of the terms here. It means that term 6 would be found by saying the sum of 6 terms minus the sum of 5 terms. So let's go ahead and do that. So that's all really we have to find. So I'm just going to put it in like that. So sum of 6 terms, let's substitute 6 into our sum formula. So that is 4 times our 6 all squared plus 1. And we're going to subtract that by that. But you see, they have 2 terms. So I'm just going to protect it with brackets. So that is 4 multiplied by 5 all squared and then plus 1. And you just have to actually find that. And that's your answer. Okay, so just to ensure that we do get marks if they separately want to see what exactly the sum of 6 terms is and the sum of 5 terms, I'm just going to do it like that. So the sum of 6 terms is 143 minus, and if you change that to a 5, sum of 5 terms is 99. So 143 minus 99 is going to get you to your answer, which is just the sum of 6 terms is 44. And that is our answer for that question. Okay, moving on to the next question. Okay, then question 3.2 says, for which values of x will the following series converge? So let's understand what should happen for a series to converge. Okay, so we know that for series to converge, a geometric series, of course, then your ratio needs to be either greater than -1 but less than 1. Okay, and the idea behind converging series is when a series converges, you look at the terms. Okay, I'll give you an example of a converging series. Something like 1 plus a half plus 1/4 plus 1/8 plus 1/16. What is actually happening to this series is that as we get to the next term, each consecutive term, right, gets closer and closer to a particular number. In this case, that number is 0, okay? But it will never actually become 0. And the idea behind that is, think about it like, let's say you have a cake. No, let's actually use something more simple. Let's say a slice of bread. And you cut that bread. So this is one whole. So we're just recording what this slice of bread is going to be, the fraction of it, as we cut it into half each time. So first it started off as a whole. If you cut it in half, you end up with just 1/2. If you cut it in half, you end up with a quarter. If you cut that quarter in half, you end up with an 8. If you cut that 8 in half, you end up with 1/16. But tell me, if you keep cutting this bread, will you eventually get nothing? Would you get no bread? No, that's not possible because you're not a magician and you cannot make things disappear. It will not become 0. It will never become 0. It may be the tiniest bit of bread, but there's still something that exists. Okay, and that's really what this is going to keep doing. It gets closer and closer to 0. That's what a series does when it converges. Okay, so I always wanted to just explain that. I know I always just gave you the formula and never really went into it, so I just decided to explain it in this video. Okay, so that's really what a converging series does. And all we're really just trying to find out is the values of x for which this is going to converge. So we know that the ratio needs to be greater than -1 but less than 1. So the next thing we would need to do to actually find out what exactly the x value should be for the series to converge is we would have to find that ratio. What exactly is that ratio? Because this series is converging, we know it's a geometric series first of all. And with a geometric series, to find the ratio, you always say the next term divided by the previous term, okay? It's not arithmetic, so we don't subtract. So next term divided by the previous term. So this one is quite simple. If you take the next term, term 3, that is 4x minus 3 cubed over, and if you take term 2, it's 4x minus 3 squared. See, these are actually quite simple to simplify. It's like x to the power of 3 divided by x to the power of 2. Okay, what happens is if the bases are the same and you're dividing, you subtract your exponents. So you end up with x to the power of 3 minus 2, which is 1. So really what I'm saying is the same thing is here on top and the same thing is on the bottom. So their exponents just get divided. And that's why we know that r is actually equal to 4x minus 3 to the power of 1, but you can just leave it like that because it's just 1 as an exponent. So that's our ratio. So we're going to substitute that into our inequality. And so we're really just saying, let me just continue here. We're saying that 4x minus 3 as our ratio must be greater than -1, but less than 1. And you're just going to solve for this inequality. So I like to call this a double inequality. It's really just two inequalities that have been put together as one. So what we're going to do is we need to solve for the x. The -3 is stopping us from doing that right now. So we're going to take it over. But because this is a double inequality, it's two inequalities really, you need to take it over on both sides. Okay, so we're going to have -1 and the 3 comes over and becomes a +3. We still have our sign. We have 4x here and then we have a 1 here. The 3 comes over, that -3 comes over and becomes a +3. So 3 minus 1 is 2 and 1 plus 3 is 4. Then we need to get rid of the 4. Again, it's a double inequality, so you're just going to do the same on the both sides. So what we're doing is actually dividing both sides by 4 to get rid of that 4. And we're going to get that x is going to be 2 over 4, is 1 over 2. And 4 over 4 is 1. So that is actually the values of x for which the series will converge. If x is greater than a half but less than 1, your series here will converge. Okay, grade 12s, I just want to add something. For this answer, I know that in the memo you would have probably seen that they said that r should not be equal to 0. Okay, so for r to be not equal to 0, if r was equal to 0, we're just looking at it like this. So let's just say we had 3 terms in a geometric pattern. So term 1, term 2, and term 3. So I'm just showing you why r cannot be equal to 0. In this case, if it is geometric, you have to find the ratio, right? Because we're really just trying to focus on the ratio. So if these are our 3 terms and we're trying to find the ratio, we'll say term 3 divided by term 2. And if it really is the ratio, it should be constant. So this should be exactly equal to term 2 divided by term 1. It should be constant. Now, if your ratio really is equal to 0, once you divide, it's equal to 0, then that would imply that either term 3 is equal to 0, then you said 0 divided by whatever value term 2 was, and then you got 0, or it should be that term 2 was equal to 0, and then you divided by whatever term 1 was, and then you got 0. But you can see how that is not possible, because if you're already saying that term 2 is equal to 0 here, and to find the ratio here, you must say term 3 divided by term 2. Well, term 2 is 0. So if you divide by 0, what happens? You're going to end up getting an undefined value. And that's the reason why we cannot let the ratio be equal to 0 in a geometric pattern. So it's something that we don't really state a lot, but it is a fact. You can't let R be equal to 0. Now, the only reason we're including this in this question is because we're specifically trying to find the x value for which the series converges. So we want to make sure we don't take a value that will make our ratio undefined. So we cannot accept any of that. So remember, it is the ratio we're referring to. It shouldn't be equal to 0. Since this is our ratio in terms of x, we're saying that 4x minus 3 must not be equal to 0. And if 4x minus 3 must not be equal to 0, we'll just solve for what x should not be here. That's 4x should not be equal to, take your negative 3 over, and then divide both sides by 4. So it really just means that x should not be equal to 3 over 4. Okay, and we have to actually state that. So yes, we do this, but we do say where x is not equal to 3 over 4, so that we don't include that in our answer. So if you're looking at your answer on a number line, you have a half and you have 1. We're saying that x needs to be greater than a half, but less than 1. Yet it must not be equal to 3 over 4, because 3 over 4 would lie in between a half and 1. It's somewhere in between here. Okay, so that is the reason we have to include that there, just because we're actually solving for x. So if you didn't include it, it's still fine. They will not penalize you for that. Okay, so that is that. Okay, so question 3.3, we have calculate the value of the sum of this series, starting where k is equal to 3, ending at 5 of this. Okay, so I would have looked at this and said, I think this is geometric because of this, but I can't say that anymore because it has k on the denominator as well. Okay, so that changes everything. That's not geometric anymore. We could go on a whole journey of finding out what exactly this is and what kind of series it is. But let's actually just focus on the fact that they only ask you to calculate the sum of the series starting where k equals 3 and ending at 5. Okay, so you can actually go ahead and expand this, because where k is equal to 3, we'll find that. Where k is equal to 4, we'll find that. And where k is equal to 5. It's just 3 terms. So you can expand and find and actually just sum it up. So where k is equal to 3, let's substitute. If you have k being equal to 3, so we have negative 1 to the power of 3 multiplied by 2 over 3. Okay, so what we're going to get there is, well, that still stays negative 1. Okay, so negative 1 to the power of 3 is negative 1 times 2 over 3. So that will give you negative 2 over 3. That's that one. Then where k is equal to 4, that's negative 1 to the power of 4 multiplied by 2 over 4. And 2 over 4 times negative 1 to the power of 4, that gives you 1. That's 1 times the same thing. So we're really just adding 2 over 4. And then where k is equal to 5, so we'll have, and I should have actually just written these down separately. So let me just say that's the answer, that's 2 over 4. And then negative 1 to the power of 5. So I get the idea, it becomes negative, positive whole time. And then we have 2 over 5. And then this is just going to be negative 1 again, because it's raised to an odd number. And that is just 2 over 5. So that's negative 2 over 5. And we just have to add these up together. So the sum of that series is going to be found by saying, if you like, you can rewrite that whole thing. It's just found by saying negative 2 over 3 plus 2 over 4 minus 2 over 5. That's all. Okay. And then you just add it up, and that is going to be your answer. So if you didn't use a calculator, you would have to ensure that all the denominators are the same. So then you will find the lowest common multiple of them and then add them up. But if you just use the calculator, your answer is just negative 17 over 30. And that is your answer. Okay, so that is the last question in question 3. And then we move on to question 4, which is on functions.